You're like, what's going on? All right, so welcome, people. A discussion today about, well, what you see here, relating angular slash rotational quantities and tangential quantities. We've talked about one specific tangential quantity so far, and we'll develop a new one and get into some tricky stuff. We're going to really start to expand our set of tools for dealing with things that rotate. And the well, how we can express quantities or express their things about their motion quantitatively. Okay, so here's sort of an older one from our last video, but here we have a disk that spins at a constant angular velocity of 2.5 radians per second. All right, so if we were to take a point here and here and here, well, every point on this line has the same angular velocity. Right? Same average angular velocity, we'll say, because they all will swing through the same angle in the same amount of time, or what we call subtend the same angle in the same amount of time. However, if we look at the red one, well, in a certain amount of time, it travels a distance, well, in what we call a period, right? That special amount of time. It travels that distance, that circumference. In the same amount of time, this green one is going to cover that longer distance, and the blue one will cover, well, the entire circumference of this whole circle. So what that means is they all have very different, not very different, but different, what we called before, tangential velocity. We could draw the red ones like that. We could draw the green ones, something like that. We could draw the blue ones, something like that. All right, the farther out these things are, the faster they have to go. And remember, we had an expression for tangential velocity, 2 pi r over t. All right, not 2 pi radians, right? This is actually the radius of the circle. This is the amount of time it takes to go around once, right? This is a distance divided by a time. So it really gives us a speed, right? So you'll see this referred to a few different ways: tangential velocity, speed, linear speed, tangential speed, anything about how fast it's going. It's not the only way that's different is if they say angular velocity. That's different. Okay. Oh, well, I guess we just spilled the beans here. Tangential velocity depends on radius. Radius. Come on, you can do it. Right, and so, you know, we said, like, well, we had this expression for theta, right? And we said that theta is, let me actually kind of restart that. We have an expression, this one that we use here, we can sort of generally say that the speed doesn't have to be the whole circumference and the whole amount of time it takes to go around, but we could say it's equal to the distance traveled on some arc, right? We could say that, you know, if the blue one, let's say, starts here and ends here, well, we have this theta, and we have that arc length there, and here's r, right, the radius of the path. Well, remember, we said that s is r times theta, right? That segment length or arc length is r theta. And or you know, I guess we could call it delta theta. And what you might notice is that we just came up with something that we defined last time, and that is, well, omega, right? Oh yeah, look. Omega is delta theta over t. So that means that we can relate tangential speed, linear speed, tangential velocity, whatever you want to call it, v, t as, well, r times omega. Okay? And it makes sense to look at our diagram here. Well, these things all have the same omega, but the green one's radius is bigger than the red one's radius, so it's tangential speed, it's linear speed, it's tangential velocity, it's speed, it's whatever you want to call it, has to be bigger than the red ones. The blue one, again, same angular velocity, but larger radius, has to have the bigger speed. Okay? Now remember, how do I get rid of all this stuff? Oh boy. Go back. Remember that, well, radius measured in meters, omega measured in radians per second. But radians really are not a physical unit. That's a dimensionless thing. It's like saying, it's kind of like saying how many rotations? Well, 4, right? So it's not a real, it's not actually a unit. But it, so what I'm getting at is for our linear speed, we do end up with the units just like we used to, meters per second. The radians just disappears because it's not actually a unit. Okay? Fair enough? Okay. Now, here's a pretty sweet drawing of a helicopter. This blade spins all the way around once every 0.154 seconds. Let's find an angular velocity. Well, that's nothing new. That's what we did last time. And we're really finding an average angular velocity, delta theta over t. And delta theta all the way around. Well, remember, we've got to make that a number of radians in 0.154 seconds. So our average angular velocity, 2 pi. So can you hear me like breathing now? It's because I have this crazy headset on with like the microphone right in my face. 154. 40, 40.8 radians per second. Yes, okay. Let's find the tangential speed of points 1 and 2 on the blade. And we'll say that point 1 is out here, where we'll say that this blade is, I don't know, let's call it 13 meters long. All right, and then we'll say point 2 is right here, and we'll say that it's, let's call it 3 meters from the end. There's point 2. Okay, so point 1, the tangential speed. Well, r omega. Average, sure. Well, that becomes, I guess, pretty straightforward, except for the fact that, well, our R is 6.5 meters. You okay with that? Right? Because here's R. And 40.8 radians per second. So 40.8 times 6.5, 265 meters per second. All right, for point 2, well, same thing, r omega, same angular velocity. All right, except here, well, our radius, 3.5 meters by my math, right? Again, we want from here to here, and that's 3 meters from the end, and the end is 6.5 meters away. So yeah, there's 3.5 meters times that same 40.8 radians per second. And this thing, 143. Okay, so definitely different speeds, even when things have the same angular velocity. Fair enough? Okay. Okay, yeah. Now, let's shut the engines down. The blade slows to an angular velocity of 5 revolutions per second over the next amount of time, 7.2 seconds, fine. All right. Let's find the blade's angular acceleration. Okay, so that, going back a day, alpha delta omega over t, right? And remember our initial was 40.8 radians per second. Well, we now need our final. It goes to 5 revolutions per second. And let's see, 1 revolution is 2 pi radians. So omega final is 5, well, 10 times pi, duh, 31.4 radians per second. Okay, so this is, let's see, omega minus omega naught over t, which is omega minus omega naught, negative 9.4, right? Negative 9.4 radians per second over 7.2 seconds. Okay with that? 9, right? Yeah. So 9.4 divided by 7.2. Negative 1.31, or yeah, sure, 1.31 radians per second per second. So at this, I don't know where I left you, I had an interruption. At this instant, this point, let's say that the rotor is rotating that way. This point is moving that way. All right. So, I don't know, any point on the blade or the rotor, or whatever you want to call it, moves tangent to the path, right? However, this thing we just said is the blade slows down, all right? So we can actually draw that, a vector representing its acceleration, and acceleration is going to look like this. And that's tangent to the curve too. All right, for an object to slow down, remember, if it's moving in one direction, it's got to accelerate in the opposite direction. Okay? I'll say, but accelerates in the opposite direction of its motion. Is that correct grammar? I don't know. All right, so we now have this thing we can call, well, certainly we have this angular acceleration, but that can lead to a tangential acceleration. All right? So here's two objects not connected on some rigid thing like this, but just two objects moving in a circle of the on the same path. And let's call this object 1. And object 1, we'll say they're going this way, right? So their angular velocity, we could say, looks like that. So this thing is moving, has a tangential velocity like that. And we just said, you know, we're saying, okay, object 1 slows down. Well, that means its acceleration has to be in that direction, right? A is opposite direction of V. Okay, and object 2, let's call this object 2 over here. Well, it's moving this way, right, tangent to the curve. But it speeds up. Well, that means that this one has an acceleration that looks like that. right? Fair enough. So here's a now like a disc, like a turntable or a a record or a CD. You've never heard of any of these things. And this thing changes angular velocity at a constant rate. Translation changes angular velocity at a constant rate. So has a constant angular acceleration. Well, that means that every point on this line has the same angular acceleration. Every point on that line will change angular velocity at the same rate. All right, but every point on that line is going to have a different, tangential acceleration. Even if their angular accelerations are the same thing. So tangential acceleration is really just, we do that the same way we do any acceleration. Well, almost any acceleration. You'll see what I mean in a minute. Right? We just look at the rate of change of velocity, which we can write as Vt minus Vt naught over t. Well, how do we write tangential velocity? Remember from a couple of pages ago, that's r omega minus r omega naught over t. Or we can factor out that r and write it like this if we want to, which I do. And then what's this? Well, that's the rate of change of angular velocity. Well, that's angular acceleration. So that means that we can write tangential acceleration as r alpha. So the farther out you are from the middle, the bigger your tangential acceleration. Because the farther out you are from the middle, remember, where is it? There we are. The farther out you are from the middle, the bigger your tangential speed. So the faster you're going out towards the outside, well, that really means the more your speed will change. So therefore, the bigger acceleration you have. Okay, so the nice thing about these is they look, and by these I mean this and this. Vt is r omega, right? We can take the tangential quantity and relate it to the angular quantity with radius. And just so we're sure to go back, that's what this is all about. It's about relating angular / rotational stuff and tangential stuff. Okay? Okay. So the engine's shut down. The blade slows from that initial angular speed of 6.5 revolutions per second to an angular velocity of 5 revolutions per second over the next 4.2 seconds. Okay, fine. So let's find the tip of the blade's tangential acceleration. All right, so I think this is the same, it's really the same stuff we did before. If we want, some of it's the same. If we want tangential acceleration, that's r alpha. Okay? Or, well, let's see. At is r, and alpha is delta omega over t. All right, and let's see. We said a minute ago that this thing is 13 meters long. That green dot doesn't belong there anymore. See ya. We want, notice it says the tip of the blade's angular acceleration. So that's going to be 6.5 meters. Delta omega, well, check this out, is negative 1.5 revolutions per second over 4.2 seconds. But then I can right in here do this. In 1 revolution, there's 2 pi radians. So we okay with the fact that delta omega is negative 1.5 revolutions per second? It goes from 6.5 to 5.0. And then these revolutions go at those revolutions. And we end up with, in here, radians per second, radians per second squared. But then here gives us meters times that, meters per second, or meters per second squared. Good. So we're back to a place where we can express tangential acceleration in meters per second squared. Now, if it's easier for you separately to say, okay, delta omega is negative 1.5 revolutions per second, and then in 1 revolution there's 2 pi radians, and find delta omega just in radians per second, and then plug that number into here instead of doing the conversion in the work like I'm doing. Obviously that's fine. I'm just doing it in one step here. All right, so let's see, I'm going to do 1.5 times 2 pi divided by 4.2, but then times the 6.5 meter radius, and I get 14, I'll round up to 15, 14.6 I get, but 15 meters per second squared. Okay? That's actually its average tangential acceleration, right? Because we're using 2 different omegas. All right, so it's an average value, yeah, over that interval. Okay? Okay. Well, remember, we started talking about circular motion. We started talking about, so let me say this, uniform circular motion talks about things that move in circles at constant speeds. All right, and when they do that, we said that, well, they're still accelerating. Even things that move at constant speeds can be accelerating if they change direction, right? And so we said, well, for things that move in circles, even if they don't change speed, they do have an acceleration that points towards the center of the circle. That's our old pal, centripetal acceleration. So we just got through talking about tangential acceleration, which is totally different than this centripetal one. All right, so let's take an example here where something's moving around a circle in that direction. And at this point, it's moving this way. There's VT, right? And let's say at this point, let's assume this object is, what do you want? Speeding up or slowing down? Speeding up or slowing down? Whoever yells loudest gets it. Fine, speeding up. Oh. So this is like a non-uniform circular motion where we have 2 parts of acceleration, right? We have the fact that this thing is both changing direction and changing speed. All right, and there's some component. What I'll do is redraw that point. If this thing is, well, like we said, moving this way, right, there's some component of its acceleration that points in the direction of motion. That's why it speeds up. But there's also got to be some component of acceleration that points inward, that does the changing of direction part. And then this, oh boy, is a total. What do you think about that? So if we want to find, oh boy, a total, let's call this, I don't know, why don't we call this net acceleration? Because this means tangential. I don't want to use another T to mean total. So here's the sum of the acceleration, the total acceleration. And we could say, of course, that the net acceleration is the Pythagoreization of those things, at squared plus ac squared. Now, this AC, remember, how do we find centripetal acceleration? Remember that? Well, but we now have an expression for tangential velocity, right? R omega. It's VT squared, so it's that thing squared. So that's R squared omega squared. Well, I'll just write that. R squared omega squared over R. So that means that here's a new expression for centripetal acceleration. R omega squared. And look, the units still work out, right? Because R is in meters. Omega is in radians per second squared. So that means it's in radian. Well, omega squared is radians squared per second squared. But the radians aren't a real unit. They're just a way of expressing angular displacement. So yep, meters per second squared still works out for acceleration. All right. So now, with this in mind, let me take this stuff and shrink. Yeah, sure. Now we can say that if we want to express the total acceleration, it's the square root of AT. Well, that was R alpha, right? Squared plus AC squared, and AC is R omega squared, right? So I'm just taking each of these and substituting in for our new formula, new formulas for each of those components. And sure, you could factor out some R's here and all that stuff, but, well, I guess why not? So you'll see this sometimes. This would be R squared alpha squared plus R squared omega to the fourth. So that would be R squared alpha squared plus omega quadrupled. Nah, whatever, you get me. And then look, we can pull this out. That's a square root of R squared. So you can see it, or you can use it if you choose, like this. But don't just then unsquared. Yeah, you can't. Whoops, sorry, like I just did. That's not the same as this. This part is not the same as alpha plus omega squared. It's not. Okay? So, you know, which version of this do you want to use? I mean, the bottom line is you got to know, you got to be able to, you got to know this. The acceleration, total acceleration for an object that's moving in a circle and changing speed has two components, and those two components are perpendicular, and you can find the net acceleration by doing Pythagorean theorem. All right, you could, of course, also find one of these angles doing some trig, right? So if that's Hey, Ryan Flatley. Yeah. Folks, I'm going to leave this here for now. When I see you next, we'll go over these next two problems. Okay. Bye.